Hi, let's now start Module 6, Participation of Renewables in Electricity Market, with its first block, what is a market participation strategy? For that, we need to introduce our basic setup. Let's assume that the students in the course 31761 decided together and start an energy trading company. This company is Rogue Trading, which we already met in the previous modules. We'll abbreviate it by RT. Then I convince you to invest in generation assets, energy generation assets. This wind farm actually consists of a single four-headed wind turbine, which is represented here, with a nominal capacity of 350 megawatts. I think we can fairly agree on the fact this cannot be realistic, at least for the capacity, but in terms of a four-headed wind turbine, it actually exists. There is one engineered by Vestas and another test on Riise campus in Roskilde. Our energy production is to be sold through the Nord Pool, Western Denmark area, DK1. And finally, we'll have balanced responsibility, which means that we'll be financially responsible for any deviation between contracts through the day-ahead market clearing and actual delivery of energy in real time. From early 2016, we gathered data and we're now going to design some offering strategies to trade on the Nord Pool. Remember that since we have a wind power generation asset, any offer we may place on the market will be at zero, since you saw the impact of regulation and marginal price on offering through a previous module. And that means we'll be coming first in the supply curve in the electricity market. A consequence is that the volumes that we'll be offering will be scheduled through market clearing. The only unknown is the market price that we're going to get, and if we're actually going to deliver what we promise through market participation. How to proceed now? What should we do before to get into the market? First of all, we should get our market basics right, and that's why we've been going through the various modules from module 0 to module 5 to know about market fundamentals, the various trading floors, impact of renewables on the market, etc. Now that we are there, we need to collect a lot of data and information to eventually make informed decisions. This kind of data and information will be information about market prices, day-ahead market prices. They can be influenced by many things, which we discussed before. The local generation mix, that's going to shape the supply curve in the market. What's happening in the neighboring zone, since we have a coupling of the different market areas. The weather may impact prices, etc. Then we may collect a lot of data and go through some historical data analysis to have a good understanding of the price and volume dynamics. These price and volumes may have clear trends, clear seasonality, and we could use this knowledge at our advantage. Since we are considering a wind farm as the asset we're going to use to participate in the market, and the market is day ahead, we will most likely need forecast to have a good idea of what we are able to produce the following day when placing our offers before gate closure at noon on the previous day. Finally, we end up having to design our offering strategy, which consists in a set of energy blocks and prices for each and every market time units of the following day. For the volume, we already said that we would assume they're going to be accepted through market clearing, and for the price, this should be zero, since the marginal cost of producing a unit of wind power generation is zero, and we don't consider any kind of subsidies or support here. The type of offering strategy we may consider may be a totally improvised approach to market participation, while you name your company Rogue Trading in the first place, so that must mean something. More seriously, being pragmatic about the market, you may consider some naive strategies as a benchmark, so you may randomize offers or find some other naive way to participate in the market, and this should become a threshold. Any advanced trading strategy should do better than that. Then you may use a set of expert rules to decide on what to do and when. Again, depending on the location of your asset, being a wind farm, a solar power plant, etc., you may actually know about the wind condition, the solar conditions. For instance, for solar condition, most likely there's not going to be generation at night, and there's going to be increasing generation during the day and then decreasing again in the afternoon. And finally, which is something that we'll develop further in this module, you may want to use a well-thought optimization model. As a basis for the discussion, let's consider a sample trading day. On the 27th of March 2016, at 11 in the morning, we want to design our offering strategy. How much are we going to offer on the day-ahead market for the following day, 28th of March, from midnight to midnight? We got information from our forecast provider, which is a wind power forecast for tomorrow between midnight and midnight. We have 24 hours, and so 24 values since having hourly resolution for our forecast. These values are expressed in power between 0 and 350, the nominal capacity of our assets, but we may also see them as energy generation for each and every market time unit, since these average power values, if integrated over the hour, will directly give you the energy you're going to generate at that time. So now that we have a forecast of the energy we may be able to generate the following day, how much will you actually offer on the market? Well, the first strategy, which seemed quite straightforward, since we invest in this forecast and we receive this information, which should be the best we can know of about our production or energy generation the following day, why don't we trust the forecast? This is a very used strategy, and we're going to try it here. That means in practice that our offers for the 24 market time units of the following day, so we have I equal 1 to 24, for I being the index of the market time unit, we'll have our energy offer, EI, being equal to the forecasted power generation, since integrated power over the market time unit will make the energy block. So energy offer equal to the forecast for each and every market time unit. This table summarizes what are our offers in terms of volume for each and every market time unit, and remember that in terms of price, we'll offer at 0, since the marginal cost of producing the next unit of wind power generation is 0. These volume offers are known, and we know that they're going to be cleared as is. So this is what should be our clearing of volumes through the day-ahead market clearing. The only unknown we have here is the day-ahead market price, and we'll have that through the market clearing so as to calculate our revenues. At 2 in the afternoon, we get the market clearing for the following day. Our volumes are being scheduled, and then these are the prices that have come up of the market clearing. The prices are 24 values for each and every market time unit of the following day, and here it varies between 27 euro approximately per megawatt hour and 41 euro approximately per megawatt hour. To calculate the revenues, we simply have to calculate the clearing prices for each and every market time unit with the respective volumes that have been scheduled. So that gives revenue for the day-ahead, RDA, is equal to the sum I equal 1 to 24 of the market clearing prices lambda IS times our volumes EI. In the present case, that gives a day-ahead revenue of 88,334 euro 49 cents. Not a bad day. However, remember we've considered the forecast, and eventually the forecast and the measurements may not be equal. So that means that what we deliver eventually is not going to be equal to our contract. The definition of balanced responsibility is that you're going to be financially responsible for these deviations. Here, for example, we have the forecast that we've considered previously and that have become our schedule in red. So that's these 24 values for each and every market time unit. In black, we have the measurements that were collected throughout the day and that were collated on the same graph. For certain hours, like here, we produce less than what we got scheduled for based on our forecast. So that means in terms of imbalance, we're going to have to pay for the lack of energy to compensate for this difference. For some other hours, we actually produce more than what we've been scheduled for. And remember the principle of the balancing market. That means that for this hour, the extra energy is going to be bought, but at a price that is most likely less than the day-ahead market price. This is when you are in a two-price imbalance settlement system, as we have in the Nord Pool. So eventually, what do you think is going to happen? Are you going to receive less money than what you thought based on the day-ahead revenue calculation? Or maybe you're going to get even more money? For that, we need to look at the balancing needs and the balancing prices. These are available on the website of the system operator and the market operator. So in our case, Nord Pool, the market operator for Scandinavia, and Energinet, which is the system operator for Western Denmark Korea. You have here on this graph, for the 24 market time units, 3 series of prices. The first series of prices is a series we've seen before, is the spot price or the day-ahead market price. It's in blue here. Then we have 2 other series of prices that comes from the balancing market. There's the up-regulation price in black and the down-regulation price in red. The up-regulation price is the price to pay for those who have to compensate for the lack of energy they are not delivering. The down-regulation price is the price that you're going to receive if you produce more, and for any unit of energy you produce more than what you were scheduled for. As you can see here, the spot price is equal to the up-regulation price. And that actually reflects the situation of balancing in the system. If these 2 prices are equal, that means that we were only in a situation that was needing down-regulation. Here, over these 2 hours, all the prices are the same. So that means we're in a situation where there was no need for balancing. And if it was the opposite, that the red line was equal to the day-ahead price and the black line was going away, that means that we're in a situation where we need up-regulation. In practice, what you have to do is to consider the price series that concern you for the different market time units. If you're in a situation of down-regulation, you receive the down-regulation price. If you're in a situation where you need to up-regulate, you will pay the up-regulation price. And if you're in balance, no need to consider prices. The rules for settlement after balancing: when you're going to produce more than expected, each extra unit of energy will be sold at the down-regulation price, which we saw in the previous slide. If producing less than expected, each missing energy unit will be bought at the up-regulation price. Again, when the system is in balance, we only consider the spot price. Also, in principle, with this 2-price settlement mechanism, only those putting the system off balance will be penalized. The resulting revenue from the balancing market will be a combination of the down-regulation related revenues minus some cost for the up-regulation payments. If we were to look at the graph of slide 7 again, you remember there were some hours where we would need to up-regulate because we produce less than what we were scheduled for, and then some other hours where we would need to down-regulate since we actually produce more than what was scheduled for. Going through the balancing settlement based on the previous rules that we described, the differences between the hourly contracts and actual delivery and the balancing prices. These are the various balancing revenues that are calculated for each and every hour. When these numbers are positive, we are getting paid through the balancing market. When these numbers are negative, we have to pay through the balancing market. Here, that gives an overall balancing cost of RB equal minus 2,454.89 euro. Therefore, if we look at the two stages together, the day-ahead revenue and the balancing revenue add up to 85,879 euro and 60 cents. Are you satisfied with this revenue? Think about it. We need, for that, to have a critical eye on the revenues we are getting from the day-ahead market and the balancing market. We need to combine those. One of the benchmark idea for participation in the electricity market is the case where we have perfect information. Remember, we go in the market with a forecast for wind power generation. Here it could be solar power generation if having a solar power asset. And then we are paying or we are losing money based on forecast errors. So the case of perfect information should be the ideal revenue we get through the electricity market. If having perfect information, somehow we are directly offering the observations as if we already knew what we were going to produce. In our case, that gives a revenue of 86,627 euro and 50 cents. Obviously, the revenue from the balancing market is zero. There's no revenue, there's no payment. Since there is no forecast error, there is no deviation between contract and realization. That allows us to define a performance ratio. This should be the best revenue you can ever get from market participation. So if we scale any results, RDA plus RB, by this revenue based on perfect information, we have this performance ratio that will denote gamma, and gamma now should be less than 1 and hopefully higher than 0. Note that depending on the market rules, gamma could actually also go negative. You may want to express gamma between 0 and 1, or you may want to express it in percentage of the maximum revenue you can ever get in the market. Here, the strategy 1, let's track the forecast, has a gamma of 99.1%. It looks very good, but again, as I said, maybe if you were to implement a very naive strategy, you could already get a performance ratio of 90%. So maybe 99.1 is not so amazing. Also in practice, having perfect foresight will never happen. So is there any other way we could consider to improve our revenue? We're going to look at two very basic ideas. Just to give you a hint and for illustration, we'll have a strategy number 2, which is called increase a bit your offer. And then we'll have a proposal for strategy number 3, which is let's be bold. For strategy number 2, that we call let's tweak a bit the forecast, we're just going to make a small adjustment to the forecast, maybe because we don't trust our forecaster, maybe because we have some market knowledge that makes we want to tweak this forecast. Tweaking the forecast in practice means that mathematically our offer in terms of energy is still going to be equal to the forecast that we have originally, but multiply by a coefficient, tau, that we denote tau. Tau will most likely be close to 1, as you expect the forecast to not be completely wrong, but you would like to change a bit your offer based on your forecast. In the present case, we're going to, for instance, use tau equal 1.05, so we increase all our offers by 5%. If you look at the various volume offers, they change a little bit from the previous case, and we may use that for calculation of the day-ahead market revenue by multiplying these various values with the corresponding clearing prices. We will also go through the balancing market and have to pay for the differences between our scheduled volumes, what actually happened, times the balancing prices that we looked at before. In our case here, the day-ahead revenue is of 92,751 euro and 21 cents. We have a balancing revenue, which is negative, it's a payment, of minus 6,680 euro and 79 cents. It's a quite higher payment than before. But overall, RDA plus RB is equal to 80,070 euro and 42 cents. if we calculate the performance ratio, it's 99.3%. So that means that on that day, this strategy of tweaking the forecast brings us more revenue than just trusting the forecast. This sounds intriguing. Though, we may want to push that. We noticed that by increasing our offer, we were getting a higher performance ratio. Let's just be bold about it. And in this third strategy, we just go all in. We push it to the bounds. Instead of tweaking with the value of tau, we just offer the maximum we can ever offer, which is our nominal capacity. Mathematically, that means that our offers for each and every market time unit of the following day will be 350 megawatt hour for each and every hour. The results of this trading strategy are that we get a very high revenue from the day-ahead market. We have a very high payment from the balancing market. Obviously, you've seen before from what actually happened that we did not produce 350 megawatt hour for each and every hour of the day, so we have very high deviations. But eventually, if we combine day-ahead and balancing market, we get 86,627 euro and 50 cents, which was the revenue we got with perfect information. So our performance ratio is of 100%. It's like having perfect information. Isn't it a nice miracle? I guess this deserves a little explanation. If you were to go back to this slide with balancing prices, you've noticed that the system was never in a situation with upregulation. So if you are in a situation where you have actually promised more than what you're actually delivering, you will be yourself in a situation with upregulation, but the price for upregulation is the same as the day-ahead price, which means you're never going to be penalized. You're going to receive payment for energy you can never deliver at this lambda S price for each and every hour of the day. And eventually, through the balancing mechanism, you're only paying back at a price of lambda S, which is the same. So thanks to market knowledge, you get a revenue which is equal to perfect information while you've only been strategic about your position in the market. There are key assumptions and issues with this type of market participation strategies that we've been discussing. First of all the rest being the same, we have to consider the potential monetary consequences of what we're doing on the market. So all being the same means the prices, energy volume, and others offering strategies. Is this realistic? Do we think that whatever we do is not going to impact the market? Actually, this defines something which we call a price taker. A price taker is someone who enters the market, make decisions, so place offers in terms of volume and price, and whatever this market participant does, it doesn't affect the market outcomes. So the clearing prices, the volumes in the market, etc. Then, in contrast, we define a price maker as a market participant who is going to affect the market outcomes with its offering strategies. Also here, in the illustration we've shown, eventually with this strategy number 2 and 3, if I get some nice results, is because I kind of played the game of knowing the balancing prices in advance, which is not possible. So eventually we will have to design some optimization problems, accounting for uncertainty, to find optimal decisions to make in the market for participation strategies. Thanks for listening. Now I would like you to use the self-assessment quiz to check your understanding.